So the CCD detector has 3,600 pixels on it. So in spectroscopy, pixel number is useless. We would rather have wavelength.
Sorry.
So to determine wavelength, we use a red calibration and a green calibration laser. So how this works is that we would determine which pixel the red and the green hit on, and then we would know the wavelength of the red and the green laser. So then through math, we can determine how many nanometers each pixel represents and convert pixel number to wavelength.
So to see whether our spectrometer actually worked, we started off with a simple sample, which was food coloring.
Okay, so this experiment was based on just checking how the food coloring would, excuse me. Okay, so what we did was we tested out the food coloring, which was like red, and we realized that the light absorbed was blue light. So then it would reflect on the red light and thus, seeming red.
So why red food coloring appears red is because it absorbs blue light. So first, when we added 1 drop of food coloring, you can see that the lowest point where the most light was absorbed is blue and green. So this is because it hasn't saturated the entire solution yet, so it doesn't completely appear red. But then when we increased it to 3 drops of food coloring, it clearly absorbed the most blue light, and which makes sense because it would appear red. So in another experiment, we analyzed the chlorine contents in different water. So first we took the spectrum of chlorine and then we compared it to different types of water. So we had industrial water, sink water, soda water, and drinking fountain water. So if these types of water had chlorine, their spectrum would match up to this spectrum right here. So then what we did, once we found out that sink water, the trough right here is about at green light, which is similar to the chlorine spectrum at green light. So we concluded that sink water has the most chlorine. So another purpose of our experiment was to verify Beer-Lambert's law. This law states that absorbance is proportional to concentration. So our spectrometer didn't directly measure absorbance, it measured the relative intensity. So we converted to absorbance using this equation. So in the equation, A represents absorbance, I naught, we assumed was 1 because 100% of light was transmitted through, and I was the relative intensity measured. So then this is Beer's law, A equals epsilon BC. So A is absorbance, epsilon is the molar extinction constant, which should be the same for a material. And B is the path length, so how far the light traveled through, which is, in this case, the length of the cuvette. And C is the concentration. So first we varied the concentration of chlorine to see if Beer's law was correct. So if Beer's law was correct, there would be a linear relationship on this graph, minimum percent T versus concentration. So we did a linear regression to find the trend line and found a correlation coefficient of 0.65. So what that means is how good a fit the linear trend line is. So the closer this value is to 1, the better the fit is. So 0.65 is pretty good. And then we plotted epsilon versus concentration. So if Beer's law was correct, epsilon would be constant and there would be 0 slope. So although we didn't get 0 slope, we got pretty close to 0, 0.0447. And this was probably due to experimental error. So then we again verified it with NaCl. So again, we graphed minimum percent T versus concentration. And this time we got better data with an R-squared value of 0.75. And we again plotted epsilon versus concentration and got an even lower slope, so which is closer to Beer's law. So in conclusion, Beer's law was verified, and it was verified better by NaCl. So this is most likely because NaCl splits up into ions, which absorb more light than Cl, which is molecules. And if it absorbs more light, the spectrometer works better. So we didn't completely verify Beer's law because of experimental error. So what we noticed is any vibrations could dramatically change the spectrum, and if the cuvette was moved at all, the spectrum also changed. So in order to verify Beer's law more precisely in the future, we would need to make sure there's less vibrations and probably use more precise detectors.
Are there any questions?
Can you use this technique to detect whether water is safe to drink? Whether it's contaminated or not?
Yeah, so you could determine the spectrum of normal deionized water and compare it to what you want to test. And then if those don't line up, you know something is in the water that you're testing.
What is industrial water?
So it's like recycled water, and they added a bunch of cleaning solutions to use it.
Not potable.
Are there any other questions? Okay, thank you very much.